What you're looking at here is a Fourier series of a complex valued function, drawing out the image before you. A Fourier series can be used to approximate many different functions, and thus can draw out any picture you want, as long as it's drawn in one stroke. This is only a taste of the power of the Fourier series and transform.
Now before I get too into it, I just want to start off by saying that this video won't be too much like the last one. There won't be as many jokes, but there's good reason for that. This video I'm going to be explaining something crucial in the field of signal processing and engineering in general, and so you future engineers are going to thank me once you understand this topic better. So last video, I tried to use the Fourier transform to change the lights on my speaker. Now I ended up scrapping that completely, but it doesn't change the fact that Fourier transforms are vital. But I realize a lot of you guys probably don't know what a Fourier transform is, does, or how it works. So let's start with the basics, starting with who Fourier was. Story time. Back in the 18th and 19th century, there lived a French mathematician by the name of Joseph Fourier, and he was working on the problem of heat flow, and he came up with this famous partial differential equation called a heat equation. Shown right here is the one-dimensional version of that equation. Now he knew that for certain heat distributions, such as the cosinusoidal heat distribution, the solution was easy. The amplitude of that cosinusoid would just decay away until you have an even heat distribution all across the rod. But what a shame that most heat distributions don't look like a cosinusoid. So he had a genius idea. He said, what if I could make any function as a linear sum of sinusoids? And that's exactly what he did. Now, I'm not going to explain all the math of how it works or how Fourier came up with the Fourier series, but what I will do is explain what it does at a high level and when you might want to use it. But if you are interested in the math, I highly, highly, highly recommend the 3 Blue 1 Brown video on the topic, linked in the description. Now let's say you have a periodic function such as a square wave here. A few terms in the Fourier series provides an approximation to the original function. But as you take the limit of the sum to infinity, then the Fourier series becomes exact. Shown here is the expression for the Fourier series of the square wave shown above. Now, as you can see, just a few terms of the Fourier series provides a pretty good approximation of the original function. Sure, it's not great around the corners, but overall it's pretty good. Fourier discovered that you can do this for almost any periodic function.
Excuse me? I have a question.
Holy shit, who the frick are you?
What about non-periodic signals? A lot of the signals in the real world aren't periodic, Nathan.
Good question, I guess. The answer is that the Fourier series can only be applied on a certain interval. That interval is then cut out and then repeated indefinitely, so that your Fourier series representation of that original function becomes periodic. Take y is equal to x, for example. Let's look at what happens when you take the Fourier series on the interval from -1 to 1. What's really interesting here is that in the limit, the Fourier series representation of the original function is discontinuous, even though we're taking an infinite sum of continuous functions. Pretty crazy, right? But what does this have to do with frequencies? Well, it means that almost any function can be represented by an infinite sum of sines and cosines, where all you need to do is change 1, the frequency, and 2, the amplitude. By just changing those dials of the frequency and amplitude, you can make almost anything you want. But let's go one step further. Instead of just dealing with sines and cosines, let's move on to the complex exponential. Because as we know, the complex exponential can be decomposed into sines and cosines by using the Euler identity. But you might be thinking, why would we move to the complex exponential and make things more complicated? We are introducing exponentials and complex numbers when we can just stick with plain old simple sines and cosines. Well, I would make the argument that the complex exponential actually makes our lives a lot easier, because now, instead of having to find the Fourier coefficient for the cosines and sines separately, you can do it in one shot with the complex exponential. The complex exponential also makes it a lot easier to deal with complex valued functions, and complex functions is what allowed me to use a Fourier series to draw the intro to this video. Because as we know, complex numbers are formed of a real part and an imaginary part, and that can be represented in a 2D vector. And 2D vectors can be used to draw anything you want in a 2D space. The point is that complex numbers aren't complex. They're actually a really useful tool in the field of engineering, and they're nothing to be afraid of, I promise. I don't think I've ever used the words complex exponential as many times as I did in the last 10 minutes as I have in my entire life. Try saying complex exponential 5 times fast. Complex exponential, complex exponential, complex exponential, complex exponential, complex. Quick side note, the j in this expression is the imaginary unit, the square root of -1. It's normally represented by I, but us engineers use j because I is reserved for current. Now why is I reserved for current? I don't know, but you can't use C because that's for capacitance. On an unrelated note, L is for inductance. I don't know how to make the rules. Whew. Okay, so after that long tangent, let's get back on track. So here's the expression for the complex Fourier coefficients, where omega naught is just the natural frequency equal to 2 pi over tau. The final Fourier series is just the sum of all these Fourier coefficients multiplied by their, you guessed it, complex exponential.
Boo! You're putting everyone to sleep. What does that have to do with anything?
Man, who even are you? Freaking hobo ass living in my house telling me how to do my videos. I'm getting there, jeez. Anyway, here's the moment we've all been waiting for. Drum roll, please. Voila! The Fourier transform. Now take a long, hard, throbbing... Nope, sorry, that's not right. Those romance novels really get to you. But take a long, hard look at this. It's eerily similar to the expression for the complex Fourier coefficients, no? Well, there's good reason for that. You see, the complex Fourier coefficients gives us the amplitudes of each of the frequencies necessary to replicate a function within a certain interval. Now, if you want to find the frequencies to replicate the entire function, you just need to change the interval to that entire function, from -infinity to infinity. And that's exactly what the Fourier transform does. It gives us a scaled version of the Fourier coefficients along the entire function as its own function. Pretty wild, am I right, ladies?
Yes?
Now, I glossed over a few details there because if you look at the Fourier transform versus the Fourier coefficients, you'll notice that the Fourier coefficients are an average, whereas the Fourier transform is not. You see, the Fourier coefficients have an integral sum, and you're dividing by the time interval. It's an average. But the Fourier transform, you're not dividing by that time interval. It's not an average. And there's a reason for that, and it has to do with confidence. Let's say you have a 10 Hz sine wave, and you're only looking at a narrow portion of it. So you're not certain if it's actually 10 Hz or maybe 15 Hz. And that results in a spreading out of your frequency plot. You're just not confident that it is actually 10 Hz. But if you extend the range of your Fourier transform, then you can be more and more confident that it is actually 10 Hz because you have more and more information. See, with an average, you don't get that because the amplitude of your frequency output is constant, and you don't get those high spikes the larger your time interval, which means you don't know how confident you really are. Similarly, if your signal only persists for a short amount of time, it's as if your Fourier transform was only taken on a short interval, and then your relative confidence is pretty low. This actually has strong ties to the Heisenberg uncertainty principle, but I'm not going to get into that now. If you are interested, I highly recommend you check out another one of 3B1 Brown's videos, link in the description. Now let's talk about audio. You might have heard that all sound is made up of pure tones, and that's true, and now you know why. Those pure tones are just the sinusoids that make up the entire Fourier series of the whole signal. Last video I tried using a Fourier transform to find those lower frequency tones of some music so that I could change the lights for my speaker. I didn't end up doing that, and you can watch my last video to find out why. Small problem though. You can't use this formula that I showed you earlier on digital systems. The problem is that this formula requires that the function be piecewise continuous, and digital systems have no sense of continuity. kind of like the X-Men movies. So, what you have to do is discretize a signal. Basically, you sample it at a set frequency so that your signal becomes a set of evenly spaced out points. But you can't take an integral of a set of points. It just doesn't make sense. So, instead, we use a regular pain in the ass sum. And then you get something called the discrete Fourier transform, or DFT for short. Here's the formula for that, where omega s is equal to your angular sampling frequency, and omega k is just your summing index k times your angular sampling frequency divided by the number of samples. Why doesn't this version stretch from negative infinity to positive infinity? Well, the answer is that it's limited by the number of samples you took. So instead of stretching from negative to positive infinity, it just works over your sampled section. Now, this will spit out another discrete complex function, but complex frequencies don't really make a lot of sense because we're not living in imaginary fairyland, we're living in the real world. So, to make it real, you just need to take the magnitude and you'll get your frequencies. So here's an example of a DFT output. Basically just looks like a bunch of garbage, right? Like, how does this tell you any information about the frequencies within your signal? Well, if you take the magnitude, then each number becomes a representation of the amplitude of a certain frequency within your signal. The frequency represented by each row or bin is determined by three things. 1, the row index, which is starting at 0. 2, the sampling frequency. And 3, the number of samples taken. So for example, your first row is your DC offset, or 0 Hz, and that's because that's 0 times your sampling frequency, which is
500 Hz,
divided by the number of samples taken, which is
16.
The next row is 1 times
500 Hz,
divided by
16.
The next one times 2, then times 3, etc. However, if you look at this, you might notice something interesting. The lower half is almost a mirror image of the upper half, not including the DC offset bin. It's only off by a negative on the imaginary parts. In other words, it's a complex conjugate. This means that the lower half is useless. It provides us no new information. And this has to do with something called the Nyquist sampling theorem, which states that the maximum frequency you can measure is up to, but not including, half your sampling frequency. So in this case, I am sampling at
500 Hz,
which means I can effectively measure up to about
250
Hz. But there's a bit of an issue. If you look at the output, you'll notice that it's saying there are frequencies that are there that shouldn't be. And you might think that this is because of noise, but I'm actually generating a pure sine wave in code, so that's not an issue here. This is something called spectral leakage, and there are 3 causes. One is the uncertainty principle, which I talked about before. If your signal lasts for a short period of time, then you're more uncertain in the frequencies that make up the signal, and that results in a spreading out of your frequency plot. The second cause is if the frequency you're supplying doesn't exactly match up with the frequencies you can measure. So for example, I'm supplying a
30
Hz sine wave, but the closest frequency bin is
31
Hz. So, since there's no
30
Hz bin, it spreads out in the bins around there. The third and main cause is due to discontinuities. Now I know what you're thinking. Before I said it's not a continuous signal, it's discontinuous. So shouldn't there be discontinuities everywhere? And yeah, but stop being such a smartass. What I mean by discontinuities is specifically at the endpoints. Because the Fourier transform gives us frequencies needed to make up the signal, but when I talked about the Fourier series before, that section of the signal is then repeated indefinitely. So, if the beginning of your signal doesn't match up with the end of your signal, you're going to have a jump. And your Fourier transform then needs to account for that jump with unwanted frequencies. Okay, now hang in there with me, we're almost done. You can go back to doing nothing real soon. Now, there are ways of dealing with this. For one, you can increase the frequency resolution of your Fourier transform by increasing the number of samples taken. This will help ensure that the frequency you want to measure is as close as possible to your frequency bins. The second thing you can do is introduce something called a windowing function, also known as a tapering function or an apodization function, which is basically just something that forces the ends of your sampled signal to meet. Now, this still changes your sampled signal, so it still has spectral leakage, but that spectral leakage is minimized. Now, you might think that Fourier transforms are generally used for things like audio processing because that's what I've been talking about, and you'd be right. They're used in things like auto-tune and digital volume equalizers, but another really interesting use for Fourier transforms is the use on image processing. To use a Fourier transform on images, you need to use a slightly different version called the two-dimensional Fourier transform. And it does the same thing, just on 2 dimensions, because images are 2-dimensional. And these Fourier transforms take something from the spatial domain and translate it to the frequency domain. Now, taking a Fourier transform on an image allows you to do things such as noise reduction, adding filters, and even things like compression. Well, that's it. You're an expert. There's nothing left to talk about for Fourier transforms. Well, except I guess for duality, shift theorems, convolution, using the Fourier transform to solve partial differential equations, Heisenberg uncertainty principle, Fourier analysis. Anyway, that brings us to the end of the video. Thanks for watching. I hope you learned something new. If you did, be sure to like and subscribe.